But oh, it's not fun. Not fun at all.
It's fun for us.
And I remember now in undergrad how much I hated biochemistry or biology at the time. That takes like 30 hours a week. To try to really learn not much. It's terrible to say. Most courses, if you hurry up reading, practicing, you have skills. If you take some skill set out. Yeah. This. We're making DNA and we have skills. But
I have student, is there any data that can compute in if I use a magnetic mount?
Magnetic mount?
There are some kind of mount, two colors, so they use the memory.
So it's not bad. If they make them. But that's not a magnetic mount.
And then you have a metallic plate.
Oh,
to put in here.
in your case.
Would you like to be enlarged?
Enlarged? I'm pretty big already. Can you make me smaller? Is that possible? I like this, just my hand.
Oh, Jabit is not on camera.
Oh.
You're hidden. You need a tripod. Oh yes. If you win, if Aaron win back, then we see Jabit. Yes. Here he is. Yes. Good image. Well, at least we have some positive emotions, even if you do nothing else.
Are we working on the same code from last time?
No. We are working with the code that is not ready yet.
Oh, okay.
We will be creatively creating a new code together.
I see. But we don't have it yet.
No. I will share some part of it, but it is so simple that we can. So let's wait until we get full attendance. If you if you let's agree to wait until 6:10. If no one else appears, then we'll start going.
I'll be giving you that look. What look? The look that you look on your wrist. Oh, you have a watch. I don't know watch. So you're gonna talk to Angle. You want me to talk to Angle? No. You give up one.
Are you taking his course? Why are you going to talk to Ango?
So you have the scene. I already got it. Oh, you did? Okay. Wow, that's really easy. Oh, sure. Actually, but you also have to optimize it, right? PBD. So there's actually two. Two. I don't know. Right? So the optimize PBD. So that's to optimize geometry in PBD as well. Because we know crystal structure. Starting. Oh, okay. So they're gonna be different, right? Yes. That's we're gonna make it together. Oh, we're writing a script together.
Why not? Otherwise, it is well, it's just interesting and saves my time. Whom I'm writing to? Levi, Brandon, Jabet, Aaron, Sam. Oh, okay.
No, Sam.
Oh, it says add.
Who's Sam?
Sam Brown.
Oh, Sam Brown. My brain was going with Seth. Yeah. My brain went to Seth.
Oh, do you know about that new tool in Outlook? Oh, no, this is Google. Oh, Google has it too.
Which will make group.
No, there's like it will suggest people who to add an email based on your previous emails.
Oh, yeah.
It does it. It does.
Yeah.
And
He loves that.
who?
You love that option.
I suffer of all these auto-correcting options. Well, I send it to wrong people, and when I'm typing something, it starts auto-correcting. Like the word, I just starting the word deer, auto-correction changes to death. And if I do not, if I do not catch it, it looks like a little insulting.
Because that's what happened when you sent me the picture, right, of your home.
Did it? Oh yes. Yes.
I was like, why is Dimitri sending me this image?
I like when they correct bad words. Auto-correct it inappropriate. Go send something. Siri comes out. He also makes sense.
We are missing to put Levi on camera.
Oh, I got it.
Yes. Good.
Oh no. Oh no, my pin is off now.
So what are we going to do? How are we going to entertain ourselves in the short time? Did you get the email?
Yeah.
Do not expect it to work. We will cooperatively do something. So the I think we will not have technical problems, and I will use this button and erase the phone for help. Now we are helpless.
As if we weren't before.
So last time on the lab and in your glorious homework, we practically looked through correction to what? Yeah, but correction to what?
Elements.
Correction to what?
To the. Oh my gosh, Brandon, I'm going to smack you. To the matrix.
No, so there are three things. There is Hamiltonian that we correct. There is a energy that is getting corrected, and there is a wave function that is getting corrected. What did we do last time?
No.
We did corrections to the energy, eigen energies.
Oh.
And today we should put our foot into the door for correcting the wave function, the eigenvectors.
You don't have preset things?
This room does not. And it also doesn't have the second screen So if you watch the YouTube, it is very delayed. It makes maybe 1 frame per second. So it is not a true video. The one that we are doing in class, it is good. Here it will be like fragmentary. Let's remember. So we have Hamiltonian of zeros plus first order correction, and then the zeros order right, and then we need to correct orbital. Good. So the correction that we are going to add to the ground state solution is summation of k not equal to n, matrix element of perturbation Hamiltonian between k and n, divided by difference of unperturbed energies. Right? So what are we going to do? We do not have time to dive deeper into complicated systems. Let's stay with two-level system and just make practical exercise and check how good this correction is. So what we are going to do, right? So the correction of the first order is composed of the wave functions of zeros order with this expansion coefficient. First order correction to orbital n. So it is corrected from the orbital k, which is basis. Right? What will be our criterion of success? This is like not very long programming effort, but if we implement, if we do this equation for two-level system, we will find the eigenvectors corrected through perturbation theory on one hand, and on other hand, we will have eigenvectors obtained by exact diagonalization. So we need to establish a criterion of success that will tell if the corrected wave function is close enough to the exact wave function. And then we may manually scan through different values of perturbation parameter, or we can do it in a cycle as we did last time. Make sense? So we will have perturbed, then we will have exact, and we need to compare at different values of perturbation. How do we compare wave functions and check if they coincide or diverge? That's a good idea.
And the further they divert.
It's so nice idea that we...
It might almost be easier just to turn the camera.
You have several ideas, one after another. Good. I'm your cameraman. So, what are you going to do?
Get a product, and then if it's closer to 1, they're towards sign, and if they're further away, then they divert.
Mm-hmm. Okay, so we can try this one, or we can try the root mean square. Just compare elements, take squares, and if they diverge too far, then you consider them far enough. But good. So you are suggesting to do scalar product of exact and corrected, and see how far it goes away from 1.
Yeah, that might go crazily off. So.
But if they are coinciding, then it will be 1.
No, but then you have to divide by a normalization factor.
But they will be normalized.
Okay,
Okay, so plan A, scalar product. Plan B, if something doesn't work, then we can I don't know. So our plan A will be to take, say, exact star and say perturbed, and call this one criterion. And plan B will be to subtract them. Okay. So the plan, what we are going to do. This one is much more reliable than operating. So we need to agree that we will deal, if it is two-level system, there will be two wave functions, ground and excited, first and second. And if you deal with both, it will be more rigorous, but one is enough. So we will be doing on the first of them. Then we need to have exact by diagonalization. We need to have zeroth order by diagonalization without perturbation, and then first order correction. And then we will take exact and first order, not actually first order. We need to have zeros plus first, and then we will compare these two. Let's sit and program, and if it will be too long or too boring, then we can do collective editing, like one by one coming here and typing something. So what we do have by now in this draft, let me, well, this is a very simple thing that you can probably do immediately, but just in case, let me show what is already ready. So we already know that diagonal perturbation doesn't perturb wave function, right? So we set the Hamiltonian for 2 by 2 with off diagonal perturbation, and at the beginning of the code we set up numerical values. And then if you want to do exact solution, we set up the full Hamiltonian, we diagonalize it, and then we extract the elements of this U matrix, which are eigenvectors, into something that we know for sure that it is wave function psi. And just in case we will be exploring the plan B, here is the probability distribution for each basis state. So we do have exact in our plan, and earlier we have the same thing for zeroth order. So for zeroth order it will be psi 0, for exact it will be psi just without anything. And now we need to program the perturbation theory expression. So we know from this derivation that is on the board that corrections are only from these two indices not coinciding. So the diagonal corrections will be 0. The correction to the first orbital coming, first corrected orbital coming from the second zeroth order orbital. So there will be no summation because we have so small matrix. So we will have matrix element which will be matrix element divided by difference in energy. And same thing for the So right now we do have expressions for expansion coefficients for first order correction. Now we need to merge the, so we do have these coefficients, right? And now we need to merge wave functions with these coefficients, right? Multiply vector by a number. Okay. So I'm typing it in a very non-elegant way. And then we can probably write it down in the form of cycles. So what we have here by now are two criteria. The psi11 is the wave function corrected up to the first order, and psi without indices is the wave function exact. So we are looking, why we are looking for the number 2? I don't know. You can look on number 1 as well, just selecting one of the eigenvectors. And then we have two criteria to see how far these wave functions coincide or diverge. One, after Levi, is just to see their scalar product. If they coincide, it will be 1. And second, look how far the probability distribution of one and second wave function differ, just by computing it and subtracting probabilities for 1 and 2. And for the value of perturbation of 30% of the energy difference, the error is between 1 and 2%. So the scalar product is precise with deviation of about 1%, and the probability shows difference about 2%. So we can either say that we are already happy and it is enough for today, or you can make one more effort and repeat this calculation in a cycle and see how these criteria of convergence depend on the value of perturbation when they become unacceptable. Well, maybe for some situations 1% is already unacceptable. But let's just see a trend. So to do so, I am going to accumulate values into a new array, which will grow in dimension each time it iterates. And then repeat this procedure in a cycle. So here we can use same approach as we did last time. So we open a cycle. Before we start everything, we declare empty arrays for criteria. And at the end, we end cycle and plot saving and checking whether it will function. So what is interesting, I have sent the final version, and we can observe an interesting trend that we are scanning the perturbation until very large values, but until it takes the value comparable to energy offset of the states. But what we are getting in the convergence criterion of convergence, it is shows the error of 10% in criterion A, and it shows error of 25% in the criterion B. So it looks like the error accumulates slower than the perturbation grows. So it is correction for wave function behaves better than correction for energy.
What is going on?
Oh, I added to make sure that both 1 and 2 are the same. So I'm trying to figure out because they weren't. This line wasn't working. So I see why. But put this on the 2. It looks as if the scalar product is always twice or around twice greater than the other one. So method
Twice, or it is just by 1? Probably we need to do for criterion.
the ratio.
For criterion A, we need to do whatever expression you suggest, scalar product minus 1. Because one is
Oh,
1
yeah.
is a
Or absolute value. So it's not negative or positive. Because that should always be absolute value.
Yep.
So criterion A should be actually 1 or whatever it shows minus 1.
The absolute value. It should be 1 minus absolute value, right?
Or absolute value minus 1. Oh,
No, the difference should be absolute value.
oh, just in case it gets.
Yeah, if it deviates up and down.
And yes, and by now we didn't include normalization. Probably if you do perturbation and normalization, it will be even better.
But at least when we ran it without doing a loop, it looked as if you took away 1, that the conjugated method is quite smaller than the pure method. Because if your conjugation is larger than 1 and you do 1 minus negative, like if you do 1 minus a larger value, then that's negative, right? And then his method B can never be negative, right? Oh, no, it could be.
Root mean square can be negative. Or it can. Well, right now it can be negative, yes.
But I was trying to make it so both are negative. If they both deviate, they don't deviate oppositely. Because then when you plot it, if one goes up, one goes down, then you have to get twice as much area, and then you don't see as good. And it should always be going the same direction unless your concavity of the curve changes, and then that would indicate that it's getting closer.
Okay, I think I do have very simple homework that probably you can complete in a minute right now, and then just submit whenever you want. Find such value of perturbation at which the error will be less than 1%. You do see that when perturbation increases, error increases as well. If we know that we are allowed to have error no more than 1%, what is the range of applicability for perturbations theory? What I found about this camera, if you try to touch it, it will return to the direction where it is navigated by computer.
Oh, you probably don't want to do that.
No, I do not.
If you manually not this not this. So now it's I was going to try and do it like matlab command to say I want to get this element greater than whatever.
It's greater than that stop. But I was just going to increase this range to 0.01.
Your call will be disconnected.
No, it's process that one.